that the de Broglie wavelength was less than 4 times 10 to the minus 10 meters. And of course, the de Broglie wavelength is h bar over, it's h over p, not h bar. It's h over p. And p, since it's a thermalized molecule, is going to be classical 2m times the kinetic energy under the square root. And the kinetic energy, 3/2 kT. So, what we're claiming is that the de Broglie wavelength to be calculated is going to be h divided by 2m 3/2 kT and this is the point at which I personally feel very compelled to check the units to make sure I didn't have any little algebraic screw-ups. So actually off to the side, I went over here and said, well, of course, H is joules times seconds. Downstairs we have kgs, and then joules per Kelvin, kelvins, and the square root like that. Well, we can break it down to fundamental units and then it becomes obvious. This is, wait a minute, joules, not joules again. This is, of course, kg meters squared per second squared seconds divided by kgs, kgs meters squared per second squared over kelvins times kelvins under the square root. So a few things go away. The kelvins go away. One of these seconds goes away. And I think you can see that it is kg squared meters squared per second squared under the radical. So kg meters squared per second divided by kgs meters per second. And lo and behold, you get exactly what you expect. So units consistency is pretty easy to demonstrate on this one. And that says there's no obvious mistakes. Then the next thing to do is just put the correct numbers in the correct places and work it out. So let's do it over here because I need more room. So lambda de Broglie is going to be h 6.63 10 to the minus 34 divided by twice the mass. How about I write this? 2 times 16 times 1.6 times 10 to the minus 27. Does that make sense for the mass?
Yeah.
Yeah, because oxygen is element number 8 and its typical mass is oxygen 16. So a oxygen atom has 16 times the mass of a proton. I realize that it's 8 times the mass of the proton plus 8 times the mass of the neutron, but they're so bloody close to each other, who cares? And then there's two atoms per molecule. So there's the mass of the creature. And then we have 3/2, oh good, it goes away, doesn't it? 3/2 times K, 1.38 times 10 to the minus 23?
Yes.
Times 10 to the minus 23, what memory? Times, what did we say, 20? 20 degrees C. So 293 kelvins. And obviously the whole thing turns out to be in meters because we've already demonstrated that. It sure looks like here I get 10 to the minus 50. Take the square root of that, that's 10 to the minus 25. When that goes upstairs, that'll be 10 to the positive 25, so we get 10 to the minus 9, huh? So we get 6.63 divided by, these 2's are gone, so we have 2 times 16 times 1.6 times 3 times 1.38 times 293 under the square root times 10. What did we say? 10 to the 9, 10 to the minus 9 meters. So now and only now do I feel this is calculator ready. Do me a favor, do it right now, and don't include the power of 10 at all. Just tell me what you get in the square brackets, please. So lambda de Broglie, you are calculating it now for me, and just give me what's in the square brackets. 0.02 something, I think. 0.02 something. 0.026? Yes. 0.026, others? Yes. 2, 3, 4, okay. 0.026, 0.022, 0.026, times 10 what? Yeah. Minus 9, which is 9, 10, 11, so we get 2.6 times 10 to the minus 11 meters. Indeed, that is, just as we stated, significantly smaller than 4 times 10 to the minus 10. It's true. So we write that number down. Oh, it's 2.6 times 10 to the minus 11 is 2.6 to the minus 11 meters. But again, let me say to you that getting to this point and checking the units, if you did that, I'm going to be immensely happy. Working out the number is simply, what is it that they say in math? Plug and chug, right? I know you guys, if you've got the right numbers in the right place, sooner or later you'll get the right answer. It may take a few minutes longer. So, like I say, getting to there and showing you this work, that's what I'm looking for. Any questions or comments, cares or concerns? Very well. Well, today I have one problem to solve. We have a single problem to solve so that we can have the, I've got another special homework set to hand out to you. And that's the goal for today. That will leave us time on Wednesday to solve a second similar problem. So we're going to do 2 problems, one today and one on Wednesday, all related to this stuff, the quiz and all the lectures we've been doing on de Broglie, etc. First, a very, very quick review. This all got started with our lectures on de Broglie, so I'm just going to put down as a review something we just had on the board. Lambda is equal to h over p. That was the de Broglie hypothesis. Later on, we found out that lambda sub n is equal to 2L over n. That's the particle in the box. When we put a particle in the box, we discovered that for the particle to exist, it has to have a wavelength. To have a wavelength, it must have one of these particular wavelengths shown here. That leads us to the energy. Once we relate the wavelength to the momentum, and the momentum to the energy, we came up with, these are the allowed energies, which were n squared times h squared over 8 m L squared. L measures the dimension of the box. Okay, so that was the first thing we talked about, was the particle stuff in the box. And we ended up with discrete wavelengths and discrete allowed energies. Kind of a surprising note, that energy is not allowed to be 0. You put a particle in a box, it cannot be stationary. It must be moving. And we use that fact to discover that if you insist that a gross or macroscopic system be governed by these laws, the lowest energy state would sure look like zero. Next thing we discussed was the uncertainty principle, which says this, basically, delta P, delta X is greater than or equal to h bar over 2. That says that there is a certain uncertainty in the momentum and the position of a particle. It's not related to experimental technique, but that the information does not exist beyond a certain limit. Only probabilities exist. And Werner Heisenberg was able to put a number to it. If you take the product of these two, the uncertainty in momentum times position, you get h bar over 2. Similar analysis led him to the conclusion that there is also an uncertainty in energy and an uncertainty in the time that it has that particular energy, and it's the same, h bar over 2. We had a homework problem or 2, and basically one of the interesting things for us is that the minimum energy or momentum that a particle can have has to equal or be greater than the uncertainty. For example, if you have a trapped particle, its minimum energy must be equal to or greater than the uncertainty in its energy. For example, you can't have a measurement of 3 plus or minus 7. That doesn't make any sense. If you have a measurement of 3 plus or minus 3 is the maximum uncertainty that you can have. Turn it around. If you know that your uncertainty is plus or minus 3, the minimum energy you can have is 3. So that's a kind of interesting argument that we went through on molecular homework problems. Next, and now we're kind of getting into the high theory of the thing, I wrote down psi equals A plus IB. What is psi? Aha, somebody's getting right into it immediately. That's correct. It is the probability. It is related to the probability of a particle. It's related to the probability of finding a particle at a certain place in space at a certain time under certain conditions. Okay, so psi is the de Broglie wave that we seek. And what we're saying here is, remember now, we have to consider the imaginary part, that psi certainly can be complex, and in the past when we were dealing with real waves, there was no way we were going to measure anything imaginary, so we only talked about the real part of the wave function. But now, since we realize that the wave function itself is not a real thing, then the imaginary part might be there. However, to cast this into our real world, we have to consider, and what did we call that when we put the star? Conjugate, yes. A minus IB. All you have to do to conjugate something is to change any place you see an I, put in the negative I. Then we discussed this, which is psi star psi, and this can be measurable. This is somehow related to the probability, and this is proportional to the probability. Related means it has something to do with it, and we don't know exactly what. But proportional means we're getting around to being able to calculate this thing. So by using the conjugate, we can square this thing and get rid of all the imaginary parts and end up with real numbers only. Kind of an interesting thought on the side is the part that used to be imaginary that we could not measure up here actually has a shadow in the real world. So here we're talking about the wave function itself, the de Broglie wave function itself, and about some of the mathematics related to the wave function. And then we went a little bit further. Now that we've established this, we said, what is this? Integral minus infinity to infinity. And I'll put down volumes suggesting three-dimensional space now, just so that I have a generalized description of what's going on. And this, I think of this, folks, as a search for the particle. We've now described the search for the particle. If the answer to this is 0, what does that mean?
It doesn't exist
No
anymore.
particle. It's definite absence. There is no particle anywhere in the universe. If it turns out to be infinity, it's God. It's the God particle. No, let's not say it like that. Let's say it a little bit differently. What does that mean?
Everywhere. Everywhere.
It's everywhere at all times. The particle is everywhere at all times. The particle fills space. What about if it is negative? What if the answer comes out to be a negative value?
It's a wave.
Make any sense at all? Doesn't make any sense. Let's see, 0, infinity, negative. All right. Certainly can't be complex either, because we made sure of that. So, what if it equals 1? Then it has a special name. The wave function has a special name. What's it called? It's normalized. That says if you search the entire universe for the particle, you have a 100% chance of finding it. So you now have adjusted the wave function to be normal. It's been normalized. So that's normalized wave function. And of course, the probability could be described as the integral from x1 to x2 of psi squared dx. That's the probability of finding the particle between these two limits. If instead of searching all logical space, you just search some little corner of space, then you discover that the probability of finding the particle between these limits is easily calculated once the wave function has been normalized. Right, next thing we did was to just speculate that the wave function psi might look like this: AE to the I over H bar minus I over H bar times ET minus PX. Might be an interesting wave function. We discovered that d squared psi dx squared is nothing more than minus p squared over h bar squared times the original wave function back again. Furthermore, d psi dt is just differentiating actually the other term and only once, so it is equal to minus IE over h bar psi back again. Why would we do that? Because we want to use the relationship that E equals P squared over twice M plus B. E is total energy. The way we've written it on the board implies the assumption that we're talking about a non-relativistic experiment. We're using classical mechanics, and capital V represented what?
Potential.
Potential, yes. If it's an electrical problem, if it's a problem with electrical fields, and that would be electric potential. But just think of it as kinetic energy and potential energy. To make this useful, we multiplied through by the wave function psi. And you notice that we have an equation right here which includes E psi and P squared psi. So we just rearranged these two and stuck them in place there. Then we further rearranged and ended up with, where am I? I'm going to ended up with IH bar d by dt, IH bar d psi dt equals, and then it's minus h bar squared over twice m d squared psi dx squared, and then we have plus v psi. Schrodinger's equation. This is Schrodinger's equation. Essentially, F equals ma in the quantum world. From there, we quickly demonstrated that you can calculate an expectation value, which is very much like an average value for any function, not energy or momentum, as the integral over all logical space of g of x times psi squared dx. And I think as our specific example, we use the expectation value of position just x. So the expectation value is kind of like the average position of the particle. You just stick an x in there, multiply it times this creature here, integrate it, and you find out what that expectation value is. Then we simplified things. We made life even more fun and simple by breaking this down. That capital psi could be written down as, of course, a e to the minus I over h bar times et minus px. Then we wrote it as a, and I think that we did this, a e to the minus I over h bar et and e to the I p over h bar x, and separated out the time-dependent part from the spatially dependent part, like that, and referred to the spatially dependent part simply as lowercase psi e to the minus I over h bar et. Inserting that back into Schrodinger's equation and considering only the steady state case, that is, let's say for example, put the particle in the box and wait until it stabilizes in its stationary wave configuration. Once we've done that, Schrodinger's equation reduced, so I'm just going to say do a little bit of algebra, and we ended up with d squared psi dx squared plus 2m over h bar squared times e minus v psi equals 0. So here's a rearrangement of Schrodinger's equation. This time, it's in the steady state. If you're in a steady state, this equation will be somewhat more simple to use because you only have one differential in it and not two. So mathematically speaking, this would be preferable. Now, finally, we're done with our review and it's time to go on to our problem. What problem do we want to solve today? Excuse me. Same one. That is, we want to solve the particle in the box. But we already solved that problem. No, we didn't. We only got part of the solution to that problem. Now we want to get the complete solution to the particle in the box, and we're going to discover that Schrödinger is going to help us a whole bunch. He's a great guy. Okay, so let's remember the particle in the box. I'm going to redraw the box now because it is a one-dimensional box. This is the potential, V. This is space, and we're going to be a one-dimensional box, so space is x. This is where x equals 0. This is where x equals L. And our two walls, remember the important part is they're both infinitely hard, like that. So this is a slightly different representation of the particle in the box, but it's in what we call, listen folks, It's what we call energy space. You see how I work with my fingers? Energy space. This is not just space, but it's energy space. Okay, let's go back to the particle in the box. This time we'll use Schrodinger and find out the wave functions. And why? I'm going to put this down. Now we're seeking this. Psi sub n equals question mark. Last time we got the energies, wasn't that good enough? No, it wasn't. Here's an interesting, bold statement. And the years of experiments have verified that this is so. The difference is when you have the wave function that describes the particle in the box, everything that can be known is built into the wave function. Last time, the only thing we calculated was the energy. Now, when we get the wave function, we're going to have everything that's knowable. Everything that's knowable. So the reason why we're going to go one step up and work a little harder to get the wave function and not just the energy is because once we found the wave function, we are certainly done. There's nothing else you can know about the particle. So that really makes the wave function a valuable piece of information. Once you have psi, you've got everything knowable. Nothing else to do. You're done. You're definitely finished. So, one thing we know for sure, don't we, is that psi is 0 when x is less than or equal to 0 and x is greater than or equal to L. Why? Because the walls are infinitely hard. The particle is definitely between the walls. It is not at or beyond the walls. So that's what we just said right there. So we find psi between. That's what we're going to do. We're going to search in that area. Now, I'm going to write down Schrödinger's equation. It is certainly in the steady state. And as we were saying before, it is tantamount to a standing wave. Now notice what I write. I write d squared psi dx squared plus 2m over h bar squared e psi equals 0. Now, first off, this is a complete differential and not a partial differential. Why? Because psi is going to be a function of x only. We've already assured that actually in this part up here. Secondly, there is no v because where we're searching, there is no v. V is 0 between the walls, infinite everywhere else. So the equation has simplified somewhat. And I have a problem for you, an in-class problem. You knew that was coming, didn't you? You knew it. I offer you a wave function, and I ask you to test it. Hopefully it only takes a couple of minutes for you to test this thing. Take long. This function must go to 0. The function must go to 0 when x equals 0 and L. We got a serious problem though, don't we? If this is an acceptable wave function, and it must be 0 when x equals 0, then we got a problem right here, don't we? Because cosine of 0 is what? Hence, therefore, we are absolutely sure that b must be 0. B must be 0. This part of the acceptable mathematical wave function is not acceptable physically. So now our wave function is restricted to this. So now our wave function, it just becomes psi equals a sine 2me square root h bar x. And of course, this wave function is properly behaved at x equals 0, isn't it? Because when x equals 0, sine of 0 is 0. That's lovely. But we also must insist that when x is L, this is also 0. Essentially, ladies and gentlemen, we have to insist that there is a node here. That says the wave function must. But that's easy to do, because when x equals L, then 2me h bar square root L must be what? How do you make sine 0 other than when x is 0?
Some value of pi.
Some value of pi. Thank you. N pi. And of course, n starts with 1. N cannot be 0 or there will be no wave. So n starts at 1. Hence, therefore, we can solve this thing for E, square both sides of the equation and solve it for E. And I'm going to modify this in just a second. E equals n squared, h bar squared, pi squared, divided by 2m, n squared, pi squared, h bar squared over 2m, L squared. See, I forgot L is right there. L has to be there. And what we have now, ladies and gentlemen, is, of course, the eigenvalues of E. So I put an E sub n there, and wait a minute. That's what we got before, isn't it? See? Almost. Almost not the same. It is essentially the same. Why? Because we've got h bar here. And so h bar squared gives me the 4 times 2 is 8, and then gets rid of that pi squared. So it is exactly the same answer that we got before. What? We wanted all this to get the same answer we had before? Yes, but we're not done yet. First off, it's pleasing that we got the same answer that we had before, but we've got a new problem now, and that is we're searching for the wave function. So, notice here I'm going to put a subscript on psi. Now I have psi sub n is going to equal a sine 2m e sub n over h bar x. And all I did was put a subscript to say, look, if we have specific values for energy, now we're going to have only certain specific wavelengths. Let's stick this energy in there and find out what psi n is. It is a sine 2m n squared h bar squared pi squared divided by 2m L squared. This whole thing is under the square root. This gets an x. Now let me see, did I put that in properly? No, I didn't. This all goes over 2L squared, and this is the whole thing under the square root, and then we have to divide it by h bar. There, I've done it right. So the square root, the radical had to include that, and kindly things cancel out. 2m goes with 2m. H bar goes with h bar squared in here. And things simplify nicely. We now have a sine n pi x over L. A n pi x over L. Hey, isn't that great? We're almost finished. Almost finished. Yeah, we're almost done. There's one last thing to do. Can anybody spot what it is? I'll give you a hint. Listen to the word I use. There's one thing up there that is arbitrary. No. No.
N.
No. Keep guessing because there's only a few more to guess. A, yes, it's the arbitrary constant A. How do you think we're going to get at A? How do you think we're going to get at the value of A? Here's where the physicist thinks. One word, sounds like it. One word, starts with N. Normalize, good, thank you very much. So we're going to squared dv. But we can rewrite this integral in terms of our experiment. The main thing is we know the particle is between 0 and L. It makes no sense to search all of space. So the integral for us, oh, I should say leads to, the integral for us is from 0 to L, and our psi squared is going to simply be a squared sine squared of that creature. What is it? It's n pi x over L, n pi x over L dx. And once we have done that, we can have the value of A. Why? Because we must insist that there is a 100% chance of finding the particle between those two limits. The particle exists between those two values. So go ahead and do the integral. Yes?
How come it's lowercase I over there and uppercase over there?
This is the general definition here. And then for us, we put in the lowercase side because we're not dealing with a time dependent. So the only reason I put uppercase here is because that comes from the general definition. This is our specific example. Yes, ladies and gentlemen, look up the integral in your integral tables. Right? Do you haven't memorized the integral sine squared of AX? Probably not. So that's what I did. I looked it up. Turns out to be equal to a squared. And I think you were saying it right, David. What did you say?
I think it was 1 minus 1 half minus.
Well, let me
He's copywriting it, get it right.
I'm trying to remember what I said.
He's trying to remember what he said. Let me show you what I got out of the integral tables. If I had the integral of sine squared ax dx, what I got was 1/2 x minus 1 over 4a times sine of 2ax sine
That's exactly what I
of
said.
2ax. That's what I got out of the integral tables. Okay? And so for us, A is equal to n pi over L, n pi over L. So for us, the integral of psi squared dx from 0 to L turns out to be, well, of course, there's an a squared out front times 1/2 x. So 1/2 x. And then minus 1 over 4a, 1 over 4 times a. So there's an n, oops, an h to n. N pi over L times the sine of 2ax. So we have 2 n pi over L x. And this whole thing is evaluated between 0 and L. Now let me check this out before I continue. A squared 1/2 x minus L over 4 pi n sine 2 n pi over L x evaluated between 0 and L. So if I put in L for x, notice that I get then a squared times L over 2 minus, and if I put in an L for x, then it's sine of 2n pi. But 2n pi, like n pi, is always 0, isn't it? So, minus 0. Then if I put in 0, 0, and 0, minus 0. Does that make sense? You guys got quiet on that one. If I put in 0, 0 here, and 0 here. So, minus 0. So what do we have? A squared times L over 2 equals 1. A, obviously, is the root of 2 over L. We have just normalized the function. We have finished, ladies and gentlemen. Here it is. Size of n is equal to A, 2 over L, sine of n pi x over L. N can equal 1, 2, and so on, cannot equal 0. Lots of writing, so I'll wait.
Does it matter that we got rid of the cosine before we did the integral? Instead of camera?
Does it matter? No, you can get rid of it later if you wish. The integral would get uglier.
But would it still disappear at the end?
Yes, yes. At some point you would discover that. Remember, we got rid of the cosine term because when x equals 0, the cosine term has to be gone. So sooner or later you're going to discover that b must be 0 for that reason, whether it be right away or afterwards. So we've completed the task, ladies and gentlemen. This is the first thing we did. We found a differential equation, then we found a wave function that satisfied the equation. That's not good enough for us. First we find the wave function, we find the mathematically acceptable. Then we apply boundary conditions. That's when we got rid of the cosine up front. So usually applying the boundary conditions next does that. It simplifies things early. So, found the wave function, then we apply the boundary conditions, and then we normalize. That's the typical procedure, and part of it is because of what he just asked. If you apply the boundary conditions, that's when you can simplify early and cut down on your mathematical complexity. So, find the wave function, apply the boundary conditions, and normalize. The last thing is, of course, is you ask yourself, is the wave function and its derivative single valued and finite and continuous? Certainly the wave function is, and of course its derivative is too, because if you differentiate this once, what do you get? You just get a cosine term. And the cosine term certainly is single valued, continuous, and finite.
You mean you say single value?
Single valued meaning that if you have, I like to think of it in a pictorial way, that if you have the wave function psi in x, and you've got something like this, that's a single valued function. If I had something like this, notice that I have two answers at one particular spot. It's not single valued. So I think of it as a picture myself. I imagine the picture, and if I see two possible answers at any x, it is no longer single valued. Or for that matter, I shouldn't be carried away with this, but for that matter, psi x, even if the graph is like this, right, it's not single valued. Okay. So we have accomplished today's mission. We have solved a problem. Let me see if I have anything else on this. No. So now I'll come around and I'll trade you. I have a homework set. So if you guys put your in-class problems at the corner, I'll pass out the homework set and we can discuss this a little bit. It's only two simple homework problems.
Thank you. Today's the day of yellow.
Today is the day of yellow. That was the paper color today.
Here's, you said you wanted to take these?
So, you're talking about a one-dimensional box.
Homework due on Wednesday. It's just two problems, but I do want to emphasize one thing, please. Find the probability that a particle trapped in a box L wide can be found between 0.45 L and 0.55 L for the ground and first excited states. Second question says, find the expectation value of the position of the particle trapped in the box L wide, the ground first excited state. And then, I didn't quite know how to emphasize this, so I wrote at the bottom, discuss your solutions. And by that I mean compare them to each other and compare them to what you might have expected. Compare them to each other and compare them to what you might have expected. That's what I was thinking when I wrote discuss your solutions. This is why we had to finish the problem today, and we were successful. We finished the problem today. And on Wednesday, we're going to take up a similar problem. Let me tell you about Wednesday's problem. Quick hint. We're going to try to make a somewhat more real potential. This potential was an infinite box. And this time what we're going to do is we're going to have a potential that looks like this. It's a step function in energy space. And we're going to have particles that have a kinetic energy less than the potential energy. So this is a step function, this is a barrier. And the particle is coming in with a certain amount of kinetic energy, which is definitely less than the potential energy. And we're going to ask the question, what happens? That's going to be the problem on Wednesday. And maybe some more stories about Hilton Blottish. Any other questions or comments, cares or concerns at this time? Yes?
I'm sorry, going back to that problem we were on originally, I must have missed it, but why did b have to equal 0 when x equals 0?
It's gone. We had this, first off, our solution started out like this. Psi, A,
Yeah.
sine, plus B, cosine,
Yeah.
and then we apply the boundary condition that says when x equals 0, psi must be 0.
Okay.
When x equals 0, the only way to make this 0 is so
Oh, I see. Okay.
must
Gotcha.
be 0.
Gotcha.
The only way to do it is kill that term. So he asked a critical question. Any other questions? That's a good one. I'm not going to treat you like Blottish treated us.
Sure. We can take it.